Hi, this will be a little explainer video about Coffee Cup Calorimetry in advance of watching some videos of people performing the lab so that you can understand what's going on and then also complete the calculations at the end of the lab exercise done virtually. Just a quick breakdown very quickly. When we talk about Coffee Cup Calorimetry, as I often joke with my classes, we're not talking about anything particularly hidden here. The name pretty much tells us what it is. When we're talking about coffee cup, we're talking about some sort of styrofoam or polystyrene container, just to get away from a trademark name. And then calorimetry is simply the breakdown of heat and measuring. So what we're simply talking about here is using some sort of styrofoam type device to measure heat changes as you go through a process. So the way that this works is quite simple. You have a coffee cup, and that coffee cup, because it's made of a very good insulator like styrofoam, and because that styrofoam is very, very lightweight, has very little impact on what goes on inside it. It simply keeps the system inside the coffee cup from interacting much with the system outside the coffee cup and vice versa. So that the reason we use coffee cups like this is that when you put coffee or tea in there, it stays warm for a long time because the heat doesn't leave the cup, nor does the cold air affect the contents of the cup, so that the system inside the cup is pretty isolated. So what you do with the coffee cup calorimeter is you put some amount of water in there. And what you need to do, and we'll talk about the math here in a second, but what you really need at the beginning here are two pieces of data for the water. You need its mass in grams, and you need its initial temperature, usually in degrees Celsius. So you want to know what's the temperature of the water at the beginning and how much water is there. And then what we do in the lab is that we take a separate beaker somewhere, put the beaker on a hot plate, and fill that with water that is very hot. You try to get the water to about 100 degrees Celsius. And into that water you place a piece of metal. And as the metal gets into that water, it will sit there, and it also will get to about 100 degrees. And so much like with the water, what you want for the metal would be two key pieces of data. You want its mass, so you know how much of it there is, and you want to know its initial temperature as well. And its initial temperature should be pretty close to 100. What you'll then do is quickly transfer the metal by means of a string or some way of not touching it into the cold water and watch the two exchange energy. So essentially what you're going to do is take the metal from here and place it into the water. And because the metal is much hotter than the water, it will start radiating its heat into the water via what's called conduction. And conduction is simply the vibration of the really fast-moving particles in the metal into the slower vibrating particles of water. And so the water particles start to vibrate a little faster, and the metal particles start to vibrate a little slower until they come to the same temperature together. So they end up at the same final temperature. So TF, the same final temperature. So the two things together, the water and the metal, end up at the same T final. As far as doing calculations for this, fairly straightforward, but there's a lot of pieces of data that you sort of need to incorporate. I know in one of the videos it talks about the basic formula for calorimetry, which is Q equals Cm delta T. Just to recap from what you've had in your reading, Q is the heat change, how much something is gaining or losing energy. C is what's called specific heat. And that's a measure of how much something's temperature goes up when 1 gram of it receives a certain amount of energy. So it's a measure of the energy change needed to cause 1 gram to change by 1 degree Celsius. Objects that are harder to heat up take more energy to heat up 1 gram by 1 degree Celsius. Objects like metals are very easy to heat up and have very low values for this. M is simply the mass in grams, and delta T is the change in temperature which is the final temperature minus the initial. And the reason we do final minus initial is that you'll get a positive value if it's getting warmer, and a negative value if it cools. So that an object that's getting warmer is receiving energy and therefore has a positive value for Q because its heat change is going to be positive. Something that's getting cooler will have a higher initial temperature than final value, so you get a negative value, meaning the object is losing energy because it started at a certain temperature and then got cooler, meaning it lost energy when it did that. Now that works for any substance by itself, but what happens when we mix two substances together? The key idea here that maybe we're not fully aware of when we first start talking about this is that Q of one substance is going to be equal to negative Q of the other substance. What that means is the energy change for one substance is the opposite of whatever it's coming in contact with. Imagine I gave you $10. I'm now down $10 and you're up $10. So the energy change, the money change between the two of us is not equal, but it's related. I'm now down 10, you're up 10. So the amount, the magnitude of the change is the same, but the sign is the opposite. So we have the same magnitude but opposite sign going on here. And so the way that works for the metal and the water is exactly the same thing, but what we're going to take is our Q equals Cm delta T and substitute that in for both Q1 and for Q2, one of the sides for water and one of the sides for the metal. Doesn't matter where the negative goes from a mathematical perspective. And so what we end up with is C of one substance equals the mass of that substance, that doesn't equal, multiplied by delta T1 equals negative C2 M2 delta T2. So you could have C of water times the mass of water times delta T of water equals negative C of your metal, the mass of your metal, and delta T of your metal. And one of those pieces of data will be unknown. Usually in the lab that we do, what's unknown is the specific heat of the metal. That's what we don't know. And that's what we would be trying to find out. And so in investigating that would be our one unknown. So theoretically, you'd have the specific heat of water. It's a known constant, 4.184 joules per gram per degree Celsius. We already measured the mass of water. We measured both the beginning and final temperatures of water. We measured the mass of the metal. We measured both the initial and final temperatures of the metal as well. So using all those, we would simply solve for C of the metal.